Hi guys, I would like to welcome you to another episode of Science Explained with Mr. K. Today's topic is rates of reaction. I know, right? I would get normally a definition like how fast or how slow the reaction is. That's actually an explanation. It's not actually a definition of what rates of reaction is. It is actually the rate at which the concentration of the products changes, or the rate at which the concentration of the reactants changes. That would be the correct definition, guys.
Hi ladies and gentlemen, I would like to start by saying that it doesn't matter who you are, where you come from. The ability to triumph begins with you. Always. These words were said by Oprah Winfrey.
Hi ladies and gentlemen, you know Yvonne, I must say those words are powerful. I also want to sound smart. I quote, "The only person you are destined to become is the person you decide to be." These words were said by Ralph Waldo.
Must you copy everything that I'm doing?
I'll get back to you on that one. Back to the show.
Right. Now, ladies and gentlemen, when you talk about rates of reaction, you can't talk about rates of reaction and not talk about collision theory. Okay? Now, if you look at collision theory itself, particles must first collide. That's what it says. Particles must first collide. Now, you can have two particles that are like this. But for as long as there's no collision between particles, you can't really expect anything to happen, right? Now, the next thing is particles can collide and nothing happens. That situation is also possible. So what does that mean? It means particles need to collide with sufficient energy. Okay? They need to collide with sufficient energy. Now, what do I mean by energy? Each and every particle or an atom, it has what we call activation energy. Okay, what is activation energy? It is the minimum energy required to break the old bonds and form new bonds. Okay, so we need to just take note of that. Particles can still collide, but for as long as the energy is not sufficient, that will not do anything. Okay, so meaning we must have what we call activation energy. Now, energy alone cannot be enough, guys. Energy alone cannot be enough. When I started, I said we must have collision, right? But it doesn't matter. We can have any kind of collision, for as long as that collision does not have activation energy, then the collision is going to be useless. At the same time, when you look at the energy itself, even if particles have enough energy, it doesn't necessarily mean that the collision will be effective. Okay, so that brings us to something else as well that we need to take into consideration. That is correct orientation. They must have a correct orientation. What do I mean by a correct orientation? If you can remember in grade 11, we were talking about a dipole molecule, and we were talking about a nonpolar molecule. In this case, I am talking about two permanent dipoles that are colliding with each other, because they are going to collide with each other in a sense that the positive will move to a negative will move to a positive. That is a correct orientation that I'm talking about. Right. Now, if we have a collision, if we have enough energy, if we have the correct orientation, that means we are going to have effective collisions per unit time. Okay? Now, when I say that, I'm going to look at the different factors that can affect the rate of reaction. Okay. Number one, I am going to look at the temperature, guys. For particles that are non-spontaneous, right? If you heat them up, if you increase temperature, what you're going to realize is that you're also going to increase the kinetic energy. That means particles are now going to move faster. I'm sure you have noticed, especially if you've turned on the kettle, by the time it boils, the particles are colliding with the wall or the container, which is called in this case the kettle. right? So I'm sure you have observed something like that. So in this case, if you increase the temperature, you are increasing the energy, and by increasing the energy, obviously more particles are exposed to collision. Not all of them will undergo effective collision, but the ones that have the sufficient energy will undergo effective collision per unit time. Okay, that's the first thing that we're going to look at. The second thing is the concentration, guys. If you increase a concentration of a substance, you are exposing its particles to more collisions. Okay, so when we increase temperature, particles are exposed to more collisions. When you increase concentration, it also exposes particles to collisions, and then we are going to have more effective collisions per unit time. Okay, same as surface area. Okay, what do I mean by surface area? I want you to think about a granule and a powder, right? A granule is like a pill that you would get from the doctor. If you look at it, it has a fixed shape, right? And then whereas powder, it's all over the place. Now, if we have something like a granule is going to occupy a very small surface area compared to when we have powder. Powder in this case is going to occupy a large surface area. Now, the one that occupies a large surface area is the one that has particles that are exposed for collisions. Like, it provides an opportunity for more particles to do what? To undergo more effective collisions per unit time. Whereas when you look at the pill, on the other hand, which is the granule, it's going to take time. Why? Because the other substance has to first attack the outer part of the pill before it can get into the inner part. So that is why it would take time for that particular substance to do what? To react effectively. Okay, it is going to react effectively, but it's going to take more time. So the more the surface area, the more we have the increase in the rate of reaction. Okay, that's what we need to take note of. All right, and then the nature of the reactant is another factor that can affect how fast or how slow the reaction is going to be. Now, what do I mean by nature of the reactant? Guys, we have your alkali metals, you have your alkaline earth metals, you have your halogens, and you also have the noble gases, which are also called the inert gases. Now, they are called inert gases simply because they are non-reactive. So if you can take, let's say, any element from group 1 and you want to react it with an element from group 8, nothing will happen. Why? Because in group 8, those elements are non-reactive. Okay, that's why when I talk about the nature of reactant, I'm talking about that particular thing. You need to look at the chemical properties of a substance before you can decide whether we are going to have a collision and the collision is going to be effective. Now, you will realize that I am using the words more effective collisions per unit time. That's your collision theory. That's what they're expecting in the test. When you reason, if you are increasing temperature, you're exposing more particles, therefore particles are going to collide, and as they collide, we are going to have what? More collisions per unit time. So you keep on emphasizing that last sentence because that's what makes the collision theory. All right, guys, now if you have pressure, okay, when I'm talking about pressure, I'm talking about increasing and decreasing pressure. If you're increasing pressure, you are decreasing the volume. And if you are decreasing pressure, you are increasing the volume. Okay? You would realize that if you are increasing pressure, in a particular container where there's gas, because obviously when you talk about pressure, it only affects gases. It has nothing to do with your liquids and as well as solid, because you cannot compress the solid as well as liquid, but you can compress what? You can compress gas. So now when these gas particles have a very small space to move around, obviously that will tell you that we are going to have more collisions between particles. Okay, but if there's a bigger space, you will realize that no, it wouldn't make sense, because particles then are going to move freely, and then as they move freely, you will seldom get a situation where there's an effective collision per unit time. So pressure is another factor that affects the rate of reaction. And then when you look at the last one is the catalyst. Okay, what is a catalyst? Is a substance that speeds up the reaction. Okay, so now in this case, a catalyst, if you add a catalyst to a reaction, because its function is to speed up the reaction, what's going to happen is then the reaction is going to be faster. In fact, number one, it decreases the activation energy. Okay, in other words, instead of your activation energy, maybe let's say it's supposed to be 5, then once you add a catalyst, you are reducing the requirement for a reaction to take place. So meaning your activation energy will now be 4 instead of being 5. Do you get what I'm saying? Not to say that it's 5, guys. 5 is an example, but I was just trying to give you a picture of what a catalyst does. It lowers the activation energy. Okay, so it allows more particles to do what? To collide at a faster rate. So by adding a catalyst, you are increasing the rate of the reaction. Therefore, we are going to have what? More effective collisions per unit time. And this is well explained, especially when you look at Maxwell-Boltzmann, the distribution curve.
Ladies and gentlemen, we have come to the end of the lesson. I hope that you have learned a lot about rates of reaction.
Yes, yes and yes. Ladies and gentlemen, to me this is music to my ears, because I have covered this section while studying. Please guys, let's not forget to like and subscribe. Until next time. We are